Now, welcome to another session with my TangerineTiger. Please excuse the slightly echoey sound, but I'm outside in my garden room at the moment. It is raining outside and yeah, it's not a very nice day, but hey, it's a great day for doing what we're going to have to do, which is some theory and theorising. Now, we found out last time that we got what looks like the essence of a very nice machine, but I need to understand this machine before I start playing with it and using it. And so today is all about trying to decode how the machine works. Now, I'm not going to go into the actual way in which the laser works because I haven't fully decoded that yet, but I'm getting there. And sooner or later we will drill down and have a look at how the actual laser system itself works. It isn't terribly different to a glass tube laser, but the way in which it's controlled is different. I haven't got an SPT laser, but good old SPT, I love them dearly. They really are a great company because they tell you a great deal about their product. They're not shy about giving you the truth, and they have a version of it called the Zamia 30 watt, which, as you can see, is exactly the same as the unit that I've got. So I'm using their specification sheet. I mean, I spent a little bit of time looking at this sheet to try and understand what's going on. It says pump method RF excited. I know what that means, and I will explain that to you at a later date. The RF frequency, which is the thing that creates the ionized nitrogen, is something called 100 megahertz. So we've got a frequency built into this unit, which has nothing to do with the control frequency. That's a high frequency, a radio frequency, which is purely to get the ionized nitrogen. In the tube version, you would see that as the pink glow. That's the ionized nitrogen. Well, that would normally be generated by a high DC voltage, as we know in the glass tubes. Well, here it's generated by high frequency as opposed to high voltage. Wavelength, power, average power. Interesting, that word, average. We'll come back to that later because I don't fully understand that. That basically, to me, means that the average output power of this unit is 30 watts, which, as we found out last time, I thought I had a 30 watt unit, but it seems to be delivering about 38 watts. You can't make up watts. You could lose watts easily with a power meter, but you can't make them up. So what we saw was real. Now, it claims here that the output range is 0 to 30 watts. How do we control that? There's only one input, and that's this PWM input here. Somewhere inside this PWM, we are controlling the power and also the frequency of the machine, because this machine works not only with radio frequency, which is just a means of producing the laser action. Most of the time it's working with a pulsing duty cycle, not a continuous duty cycle. So let's try and understand what these terms here mean. We've got rise and fall time, duty cycle, and modulation. So those are the three terms that I'm going to be concentrating on today because I don't know, but I think they are the key features that are going to control this unit. Now, eventually, later on, I'm going to be putting my oscilloscope onto the PWM terminal and trying to find out exactly what is going on. So not only are we going to be trying to look at the electronics, which are these features here, but because the electronics don't actually tell you what's going to be happening down on the surface of your material. So there's a relationship that we need to establish between the electronics and the real world. First of all, we have something called a PWM. Now, we've set the PWM in the vendor settings to 25 kilohertz. Now, from my previous work with the glass tube and the reader controller, I know what the PWM signal looks like. It's basically a square wave. Okay, now a square wave looks like this. It starts high, it goes low, and then it goes back high again. And then it's joined onto another one and another one. So we finish up with this square wave shape. Now this square wave here represents one cycle, and we are talking about 25,000 cycles a second. And that's what 25 kilohertz is. So just to put some more detail on that, so in 1 second, if we divide 1 second by 25,000, we finish up with 0004, 4 zeros and a 4. Now let's just make some sense of that. 0.000, comma, 000. So that's a millisecond, or a thousandth of a second, and that's a microsecond, which is a millionth of a second. Okay, and we have got 1, 2, 3, 4, 3, we've got 4. So here we are, 40. 1, 2, 3, 4, 4 noughts and a 4. So we're talking about 40 microseconds for a cycle. So that's as fast as the machine can actually pulse. The problem that I had was when I sat down and looked at that, and then I looked at another part of the specification which says pulse rise stroke fall time. Now to me that implies that when I've got a square wave, I've got a square wave that does this. Where that time there, the rise time, and there the fall time, is 100 microseconds. But hang on, if that's 100 microseconds, and that's 100 microseconds, that means the pulse is going to be 200 microseconds long, but I've only got a pulse that's 40 microseconds long at 25 kilohertz. So now I'm scratching my head and thinking, do they mean microseconds or do they mean nanoseconds? Sometimes these values do get a bit scrambled up when it comes to specification sheets, because the people that write the spec sheets don't actually understand what they're talking about. So there's conundrum number one. We're getting a mismatch of data. Let's just assume that we put that problem aside for a minute and we just carry on and try and work out how do we control the power. Forget the actual frequency at the moment, let's just stay with the square wave. It clearly says on here PWM duty cycle 0 to 100%. What does that mean? Well, what that means is that whatever that height is of the square wave means I'm going to get an output of 30 watts from the unit. Am I going to get 30 watts? As I mentioned last time, look, we've got 50% of the time we've got 30 watts, and the other 50% of the time we've got 0 watts. So therefore the average of that is going to be 15 watts. Now how do I get 30 watts out of this unit? I think that this here will be expressed as 50% power on our controller, because 50% of the time we're getting power and 50% of the time we're not getting power. This is a slightly different way of using this term percent power. In the previous glass tube situation, the power represented current flow. Now it doesn't represent current flow, it represents the amount of time that the beam is on. It's on for 50% of the time here and off for 50% of the time. So if we want 30 watts out of this unit, what we've got to do is we've got to ask the power to come on and stay on for 100% of the time, and then go off and come back on again, and go off and come back on again. I mean, it's never going to go off technically, I'm just drawing it like this to illustrate the point. So here we've now got a pulse width modulation of 100%. And that's what we're seeing here. Duty cycle, 100%. The cycle is 100% on and 0% off. Now equally well, when we look at the average power that's coming out of here, it's no longer 15 watts half the time, it's 100%, 30 watts all the time. So this is like 30 watts CW, continuous wave. So this is very much the same as a glass tube where we've got continuous output. We've got no pulsing. And that is how I think I did my testing, because I set the power to 100%. So that's why I'm seeing 30 watts. Okay, now if I want to change my power in the same way that I've gone from 30 to 15 by using 50%, and instead of going 50%, we go say 10%. On, and all that time off. 10% on, off. 10% on, off. So now we've got 10% of 30 watts. So we've only got 3 watts now. So here we are with 10%, and we've got 10% of 30 watts. So we shall only have effectively an average output of 3 watts. So now hopefully you can begin to see how that by changing this ratio of the square wave, how much it's on and how much it's off, we can change the power output of the unit. And that's what this duty cycle is here. 0 to 100%. We can change the PWM duty cycle and allow more power or less power. We've got this big question mark here with the rise and fall time. We now understand what the duty cycle means. It's a means by which we can control the power that outputs from the tube. What about this other thing here, modulation? We set the vendor setting parameter to 25,000 cycles a second. Because we have chosen the RF tube within the vendor settings, so when you look at the power controls now and press advanced, you'll see that in there you have got for each layer the opportunity to specify a different frequency. So we can modulate, as they call it, the frequency between 0 and 25 kilohertz. So what effect does that have? Here's our standard 25 kilohertz that we've discussed already, and we showed that if we reduced the power percent to 10%, what we've done, we've reduced the amount of time, that element there, as 10% of the cycle. And in 10% of the cycle, we're going to finish up with 3 watts, as opposed to a full cycle of 100%, 30 watts. Now, when we halve the frequency to say 12.5 kilohertz, we've got 2 of these cycles. Now we've reduced it to 1 cycle in the same period of time. Now, when you look at this picture here, you'll see that 10% of that longer cycle represents a much longer period of time. So you might think to yourself, yeah, that means that I'm going to get 6 watts of output. It gets a little bit more complicated than that, because that isn't true. We've still got 10% of this longer period of time. So as well as this on period here being longer, this off period here is much longer as well. So the ratio is still 10%. So on average, we shall still get 3 watts, not 6 watts, out of this pulse. But however you look at it, we've had that pulse on for longer than this pulse. Therefore, we must be doing twice as much damage. We're doing twice as much damage, but we're taking longer to do that damage because the pulses are spaced further apart. Who said this was easy? I have to point this out to you because we've got these 2 forms of control. So we've got the mark space ratio control, which, as I said, is our percent power. And then we've also got this modulation control, which has a different effect. It slows down the pulses, but it actually increases the amount of time that the pulse is on for. In other words, we're likely to do more damage because we're holding the pulse on longer. Now, although the average power coming out of this is still at 10%, 3 watts, we have still got 30 watts available in every pulse. And that's the big difference between an RF pulsing system and a constant power system. Let me try and explain that in very simple terms that you can probably understand. You've seen me before doing the candle test, where I put my hand over a candle flame and I move it slowly across the flame. It doesn't hurt. If I move it very, very slowly, it certainly does hurt. All right? The point that really is taking place there is we have got a fixed amount of energy coming from the candle flame. We can share that energy across the surface of my hand depending on how fast I move my hand over the flame. I can stop my hand and use all the energy into one spot, or I can move my hand faster and I can share that energy out. Okay, so I can make, and this is the best way of imagining this, the feel on your hand. The faster you go, the less it hurts. Well, that wouldn't be the case here, because we've got 30 watts for every single pulse. We're not sharing the power out. We might be sharing the distance out. In other words, this is a 30 watt pulse here, and a 30 watt pulse here, and a 30 watt pulse here. I shall finish up burning 30 watt pulses across my hand. Right? Whereas with a constant system, I will just generate a very thin line of energy across my hand. So that's the big difference between a constant on system and a pulsing system. You won't find this stuff explained anywhere else if you go to one of the big boys' websites. They don't tell you how their machine works. All they will do will give you menus which will allow you to select these numbers, and you have no idea what they're actually doing unless you have an understanding of the basic principles of what PWM is, what duty cycle is, and what the modulation of the signal is going to create. So yes, we're still going to finish up with average 3 watts with this system, but you're going to finish up with the same powerful pulses that you are producing here as well. 30 watts. Now with the glass tube laser, there was a sort of emulation of this principle available to you in something called special mode. And there, the duty cycle wasn't called duty cycle, it was called this strange term, facula. So immediately you turn special mode on, you would get this 50% on, 50% off. You were no longer operating with continuous current. But you could get back to continuous current by changing the facula to 100%. Okay, and that just allowed this duty cycle to get longer and longer and longer. So when we start using the machine, we shall have to come back and look at this to try and understand what we're doing when we're damaging materials. Because I hope you can begin to see that changing the frequency has a different effect to changing the duty cycle. So at the moment, this is just speculation on my part, based on the knowledge that I have so far. I'm projecting what I will find and how this system works. I don't actually know, but it will become completely clear when we start looking at the signals with the oscilloscope. So we should easily be able to verify what's going on here at a single pulse when we look at it on the oscilloscope. I'm now going to show you how I think I'm going to be able to find out the relationship between what these signals are doing and what happens on our material. Here's a surface, and here's my laser beam coming in like this. Remember what the curtains effect caused? If we slow the beam down, we burn deeper. If we speed the beam up, slow it down, speed it up, slow it down, speed it up. Because we slow it down, we've got more time to do damage, and so we burn deeper. Now that's what happens with a constant power beam that is changing its speed. Slow down, faster, slow down, faster, slow down. We will generate that sort of pattern. Now that makes the laser machine a very good velocity plotter. And so what I propose to do here is do something like we're allowed to do, because it clearly says here that we can change the modulation to 0. Well, I don't want to go to 0, but what I might do is to go down to something like 500 Hertz. If I run the machine at 1000 millimeters a second with a 500 Hertz signal and 50% power, i.e. we're going to finish up with 50% on, 50% off. What sort of pattern am I going to be generating on the surface? Because on will produce a pit and off will produce nothing. So I should theoretically be able to generate this sort of pattern on the surface. Now, what sort of size pattern am I going to be expecting when I put these numbers into reality? Well, look, 1000 millimeters a second, so in 1,000ths of a second, I'm going to travel 1 millimeter. So what does 500 Hertz equal? So if I take 1 second and I divide it by 500, I get 002. That's 2 milliseconds. So that means at 500 Hertz, I'm going to travel 2 millimeters per cycle. So that's going to be very easy, because technically what I should see is 1 millimeter, 1 millimeter, and 1 millimeter. Now, whether 30 watts is enough to create sufficient damage for me to see is interesting in acrylic. I'm hoping that I should be able to see some noticeable pits. In addition to those noticeable pits, if they are sufficiently clear, I hope I might be able to examine them under the microscope and see things like this. It may well look something more like that, with curved, but it should tell us clearly, approximately, what this rise and fall time is. Now, whereas in a glass tube there is a relationship between the current flow and the power output, the watts output. So we had current flow, which was pretty linear, like this. Okay, so these are watts and these are milliamps. The milliamps go up at a steady rate and the watts do not go up at a proportional rate. Now here we've got a completely different situation, I believe, because we have got constant current and we're switching that constant current on and off to get the change of average power, because we're chopping it up. As I said, we're using what they call the duty cycle to control the power. So now I believe that what I'm going to get, I've got no idea what the current is because it's going to be constant, and say like that. But because we've got constant current, I think that what we're going to finish up with now is a graph that looks like this. 50% equals 50% of the available 30 watts. 100% equals 100% of the available 30 watts. So therefore, I'm anticipating a direct linear relationship between percent power and watts. And finally, I think one of the very, very first things we'll do when we get back onto the machine is do a mode burn. It's a very nice 6 or 7 millimeter beam, and I'm expecting to get a nice sharp mode burn into a piece of acrylic. How deep that goes will be interesting for 10 seconds, because you've seen that I can bore my way through almost 25 millimeters in 10 seconds with a 70 watt constant power laser. How far do I get through with a 30 watt laser, I wonder? So you're getting a front seat view of a mode burn. Now at the moment I haven't got the air assist on this machine hooked up, so I'm going to have to use my blower to make sure I keep the fumes away from the front here, otherwise they'll catch fire. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's not too bad. So we'll very quickly swap the ×2 for the ×3 beam expander and look at the difference. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. To be honest, if I had a tube that looked like that, I would throw it away, because that mode burn is so blunt, it's pretty useless for cutting and for engraving. So I think you can see clearly the difference in the power distribution between those two beams. They're the same beam. One has been expanded 3 times and one has been expanded twice. No competition. I'm sticking with the 2 times at the moment because that has much greater damage capability. Now the other thing that's slightly more difficult to see, but when you look around the outside of that beam you can see all the low energy density power, how it's melted and bubbled up the acrylic and not evaporated it. We've got a lot of low energy in the outer area of the beam, whereas when we look at this one, that damage around the outside is very minimal. We're concentrating a lot of the energy down the centre part of the beam, and that's what I like to see. What I've got here are 2 mode burns. I've got one that I'm going to put behind the ones I've just done. This one at the top here is from my 70 watt cloud ray tube. This one here is from our ×2 RF beam, and this one here is from our ×3 RF beam. The point I really want to make here is that for a long time I've heard some, now I don't want to call it bullshit, but effectively that's what it is, from the big boys who have always had a serious down on these cheap Chinese glass tube machines that don't last any time at all. And I've been to exhibitions and I've heard those sorts of words mentioned, but you cannot deny the facts now that I've got my hands on another type of machine which they claim to be the best in the world. Well look, a 30 watt tube is a 30 watt tube. You can't perform miracles with 30 watts. If you want to cut, you need power. So don't regard these 30 watt RF tubes as cutting machines. I never have, and now I never will do. Yes, they will cut, but they will only cut what you could cut with a K40. You know, you might be able to cut 3mm material. You might be able to cut 6mm material very, very slowly. But hey, we shall get onto that later. But the fact is, you require power to cut. This is an axe. This is a scalpel. You cannot chop a tree down with a scalpel. We'll move on from that interesting fact. I've just carried out a calibration on this machine, but what I've had to do is to block this off temporarily with a piece of card, because the airflow at this end, I was at risk of cooling the doohickey down with this high airflow. So So I've had to protect it from the airflow to get, should we say, more accurate figures. The figures are not quite what I expect. So I'll just go and plot them out and we'll take a look at the graph. Okay, please excuse the typo. We'll fix that later, but it's not important because, hey, the thing that's important is my prediction of what this tube would do is 80% wrong. This is what I thought it might do. It might produce a linear output. Yeah, this is sort of linear, but it's not good enough to really be called linear. I mean, let's be fair, it's probably about 30% adrift. So something is not quite happening as I expected and described to you previously. At the moment, I think this is a 25 kilohertz signal, and it's operating with proportionate control. And proportionate control should be, as I described to you earlier, linear. The fact that it's not, there's only one way to find out what's going on, and that's to have a look at the PWM signal. There's my little oscilloscope that feeds into my laptop and gives us the opportunity to see what's happening to the PWM signal. What we've got here is 0 volts, and somewhere just about here we've got 5 volts. Okay, so now I've got the system currently set to 50% power. In other words, I'm expecting to see half the peaks high and half the peaks low. So let's just check. We run a program and we can clearly see here we've got 50% high and 50% low. So that's working a treat. The only problem is we've got 2 cycles per division, and the divisions across the bottom there say they are 0.1 milliseconds. If we've got 0.1 milliseconds for an interval, that means one cycle is taking 0.05 of a millisecond. So if I take 1 second and divide it by 0.000, which is a millisecond, 0, that one, 5, so 4 noughts 0, 5, the answer comes out at 20,000 hertz. In other words, 20 kilohertz. Now, I thought I'd got this system set to 25,000. So we're going to have to now go back and look into the vendor settings and find out what is it that is set to 20,000. Right, we're going to vendor settings, read. So there's my problem. Check glass tube, 25 kilohertz, 1 and 99. We could set that to 100. Right. So I've hopefully got this set up now with 40 microsecond for 2 divisions. In other words, 20 microseconds per division. Now, if you remember when we did the calculations for 25 kilohertz, it was 40 microseconds per complete cycle. So here we should see 1 division up and 1 division down. There's our 50-50, 50% PWM. It goes to the same level every time. That looks like about 4 and 4.5 volts. So we now change to 10%. So now we should see just a little bit high and the rest of it low. Like that. So this is exactly as I described it to you. This is the duty cycle. 10% on, 90% off. And that 10% there represents the 10% that you're selecting on the keyboard. If we select 99%, we should see a little division. Let's just resample again, 99%. And there it is, at just over 4.5 volts. So there's no change in the signal level going to the RF unit. The PWM is purely changing the duty cycle to change the amount of power that we're putting into the pulse. And we're either putting long pulses or short pulses, but they're all the same power. So on this machine it looks as though we cannot change the power by changing the level of the signal. We can only change the power by the ratio of the signal length. I'm just going to draw a circle, put the padlock on, and I'll make that circle 10 millimeters diameter. Now 10 millimeters diameter means it's got just over 30 millimeters of circumference. We'll put this into a cut layer. We'll make the speed about 2 millimeters a second. Then it will be 15 seconds roughly to run round the circle. Let's set the power to 50% because we know what 50% looks like on the screen. 50, 50. And we're going to this advanced mode now. The only one that's available to us is number 1, and it says laser frequency. Well, we'll put that tick, and this time we'll change that to, we had it to 25 kilohertz before, which took up 2 increments on the screen. Let's take it down to 12.5 as we did with our example, 12.5 kilohertz, and then we should realise that it will take up 4 increments on the screen. So now, if I'm seeing this right, we should see full signal level 5 volts, and too high and too low. And there we go, just as predicted. Too high, too low. So really, we've only got 2 controls for this machine. We've got our power control, which, as I mentioned to you before, changes the mark space ratio. This is 50% power, so it's 50% high, 50% low. If we change it to 10% power, we get 10% high, 90% low. But there is a second function, which is the modulation, which is the frequency, and that allows us to change the length of the pulse combined with a slow repetition rate. So we can either have a fast repetition of a pulse at 25 kilohertz, or we can have a much longer pulse, getting closer to continuous mode, long or short pulses at 25 kilohertz, or long or short pulses at anything in between. We've got control of the frequency, we've got control of the pulse width, and that's it. Here we are at the end of this session, I think. Hang on, let's just turn this noise off. Oh my goodness me, my ears are actually buzzing. I'm going to have to do a lot more than just a little bit of a cardboard deflector. So in a strange sort of way, there's a lot less to understand on this machine than there was on the glass tube machine. Perhaps I'm saying that in hindsight, now that I know a lot more about the glass tube machine. But it seems as though this is going to be simpler. So that's already converted it to grayscale already as it's brought it in. So let's have a look to see whether or not we have the option. Oh yes, we do. We've still got our frequency control. Now we've got our output direct, which is grayscale. So I can experiment with grayscale engraving on this machine because I've got a lot more control, hopefully at the pixel level. So we've got lots and lots of options that we can play with here for images. We do some cutting. I'm told that this system produces fantastic polished edges on acrylic. Am I cynical? I think I was born with it in my DNA. We shall have to see and find out just how good it is at what other people claim for this type of machine. Now we've got a machine that we understand and it's working, almost. I've still got a few things to tidy up on this machine before we start working it in earnest. But hey, we're nearly there. We understand all the tools that we've got to play with now, which is great. So thank you very much for your time and your patience, and I shall see you in the next session.